Hello to all of you. Thank you very much for joining us in this webinar session. We are very glad to have you here with us today. Just before starting, a few information on this session. You will have a Q&A session at the end of the webinar. So during our presentation, you can submit your questions in the Q&A panel, and we will try to answer as much of them at the end. Concerning the slides we are presenting, so you will get a post-webinar survey, and when clicking yes, you can ask us to submit the slides, which you will receive a few days after. And according your screen arrangement, you can adjust your settings. If you prefer, for example, a full screen layout, just tick this option, and you will have the webinar in a full screen. So, time to start with the session. The topic of this webinar is hidden leaks, hidden costs, detect leaks and save money. This webinar is suitable for all of you. Either you have perhaps some experience already with leak detection or not. It will suit you, and it will take about 45 minutes.
So thank you for your kind introduction, Stephanie. So just to tell the audience who you are. So Stephanie Wasitz is born in Germany and holds a Master for International Business from the University of Applied Sciences in Zwickau. Her education was with a strong focus on marketing and finances. And this dual language, this bilingual course, has enabled her to move to the beautiful area of southern France immediately after the courses and take a first position at a French vacuum company, specializing in many branches of vacuum technology, including pumps, cleaning procedures, residual gas analysis, and also leak detection, which is today our topic. And since more than 7 years, Stephanie is with Bosch, and she started as a market manager for various industries, including semiconductor, mobility, and various others. And this experience has enabled her to take the position as a sales manager, head of national sales in France. Happy to have us to have you with us, Stephanie.
Thank you very much, Rudi. I will also have the pleasure to present you. So it's really a pleasure to present together today. So Dr. Rudolf Konvichny did his study at the TU in Munich and has a PhD in chemistry. Then he started his career directly in the vacuum technology, and he worked since 1994 in sales for vacuum technologies, leak detection, and mass spectrometry. And since 2003, he is more working on the application side. So he is application support for Pfeiffer Vacuum, for leak detection, especially, and vacuum technologies. And since more than 15 years, he provides trainings, especially for leak detection. So he is a great expert on leak detection, and the trainings are provided, yes, for Pfeiffer Vacuum, but also for the German Society of Engineers and the German DGZFP, which is the Deutsche Gesellschaft für Zerstörungsfreie Prüfung, which is an institute for non-destructive testing. And he is also very impressive, head of the technical committee for leak detection of the Committee for Non-Destructive Testing in Germany. And yeah, besides all this stuff about leak detection in his free time, he likes to listen to music, especially with his vinyl record player, which also has a vacuum pump inside, which is not such a surprise to me.
Yeah, politically correct record player. Thank you for your introduction, Stephanie. Thank you for the kind words.
Yes, we will move on now with some information on what you can expect from this webinar. So our target is to provide relevance of leak detection to you. So that means giving you some more understanding about the role of leak testing and achieving cost savings. Also, we want to provide examples and calculations to give you some real-life examples which will show the impact of leaks and the costs out of that. to give you also practical guidance with some explanations on how to recognize leaks, and to guide you on the methods for leak detection you can choose.
Exactly. So before going into applications, let us start with some fundamentals. So generally, what is a leak? I'm afraid that every one of us has already experienced practical consequences of leaks. The first example that we have picked is a flat bicycle tire. So hopefully this happened not too far away from your home. Riding without the inflation is difficult. The consequences of this defect are not very drastic, so you have to walk, and this can be tolerated by the majority of us. What is much more dramatic is the second picture that we have shown. So this is the explosion of the Zeppelin back in 1937 in Lakehurst. So the filling was with hydrogen, and the escape of this gas and this inflammable gas has caused a fire, which has cost dozens of lives of human beings. So these are two examples for defects of gases, so emanating gases. Of course, other media can escape as well. So we have just taken as an image the escape of water from a pipe, but also other liquid media can escape. For example, refrigerants or also hydrocarbons having effects on the environment. So if a hazardous substance escapes, that there may be corrosion, there may be a greenhouse effect, whatever will be the consequence of this defect, of this leak. So I have already used some expressions in order to describe a leakage, a hole, a defect, a size, whatever. So in order to connect with you, to find the right words, we would be interested, how do you describe a leak? Do you describe it in a technical way? Do you use a phenomenological description? I see a sweating of a liquid or whatever. Or in which way are you describing a leak? Are you working in the vacuum industry? So do you see a change in the base pressure of the process pressure, for example? Or do you work in the refrigeration and air conditioning industry? In this community, leaks are mainly described by mass loss over time. Or what is your way of describing leaks? How can we connect to you? Please let us know. So I see people answering.
Yeah, let's see.
The bar graphs are moving. Yeah.
Okay.
We'll give you a couple of seconds more.
Also, you can use the chat function if you have the reply you want to provide is not in this list. Just let us know via the chat function.
Yes, please do so. Yeah, I don't see any changes anymore, so I think we can close this poll and say thank you. So it's interesting that nobody is using the ingress protection types, for example. So this would be common for example, automotive applications. Electromobility uses this phenomenological description of leaks in order to avoid the ingress of rainwater, for example, into a battery pack. The majority of you seems to be familiar with leak detection already, because you're describing defects in units and also in vacuum technology, changing a base pressure, for example. Interesting results. Thank you very much for sharing with us.
Yeah, looks like we have a lot of experienced people here with us. That's great. I want now to come back to some definitions together with you, Rudi. So on my side, I had to check in an online encyclopedia to see how they describe a leak. And what I found was the following description. So a leak is a way, usually an opening for a fluid to escape a container or a fluid containing system, which could be a tank or a ship's hull, through which the content of the container can escape or outside matter can enter the container. What do you think about that, Rudi?
Yeah, you are from Creative France and you're from a generation who is a digital native. So when I started my courses, the internet did not yet exist. So I was brought up with paperwork, and I'm in Germany, so Germans love regulations. And there is one which also describes the vocabulary for leak detection. And in this regulation, which I can only recommend, for example, if you need to write a work instruction, if you need to communicate with international partners in order to find the right wording, it's a valuable tool. And in this regulation, generally in non-destructive testing, a leak is described as a hole, a porosity, any element, any structure in a wall of an object, which allows gas, of course this applies also for other media, to pass from one side of the wall to the other side of the wall. And the driving force for this media transport can be either a pressure change or also a concentration difference across the wall. So also with no total pressure change, if the concentration is different, also this will lead to transport of media. So this is how regulations are describing the leakage. A phenomenological description of a leak could also be done by bubble testing. In our first example, we have shown you a flat bicycle tire. So you would remove the tire and dunk it into water. And if you see something like that, that's roughly 1 bubble per second with a diameter of 2 to 3 millimeters. This would correspond to a leakage rate of roughly 10 to the minus 2 millibar liter per second. And this defect would make your bicycle tire flat in roughly a long weekend. There are other applications, other fields of industry with larger or smaller leakage rates. We have picked one example for a larger leakage rate. So for example, this fuel cell stack here can be still functional at a leakage rate of 10 to the minus 1 millibar liter per second. But if we dunk it, this would correspond to 10 bubbles per second. And this is a defect which makes a bicycle fly a TED in few hours, so far less than a day. Now, this is already leakage. Stephanie, do we need anything else to understand the concept?
Yes, I think we should go a bit back to pressure and vacuum. So let's start with what is pressure. So pressure can be described as a force which is exerted on a certain area. As you can see on the picture, pushing with your nail with your finger on a nail on a surface, you exert a certain pressure on this nail. Another example is imagining the air which surrounds us all is pushing on everything and all the time. So that is what we call atmospheric pressure. Now going more to vacuum. So what is vacuum? Vacuum is described as a space where pressure is lower than this atmospheric pressure, which I have just mentioned. So we can imagine here an example like a gas bottle or a bottle which is closed and the air somehow is removed of this bottle. So we have less air in this bottle, means less pressure. Another example from our lives is imagining in mountain areas such as at the top of the Mount Everest. You have very low pressure there compared to atmospheric pressure, which is around 1013 millibar. At the top of the Mount Everest, you have around 300 millibar. So less pressure, less oxygen. And we have quite a lot of common units which describe pressure and vacuum. So here we have selected 3 of them. The first one is Pascal. Pascal is a standard unit of pressure, and lower values, so lower values of Pascal will mean higher vacuum. Another one is Torr, which comes from the Italian physicist and mathematician Evangelista Torricelli, who used the height of a mercury column to measure pressure. And also a very common one, especially in Europe, is millibar, which is used in the same way as hectopascal. And also we can just please come back. A last point about especially vacuum ranges. We divide different categories of vacuum. So when we talk about pressures starting from 1000 millibar going to 1 millibar, we describe this as low vacuum. Medium vacuum is more around 1 millibar to 10 to the minus 3. millibar. High vacuum generally described in the range of 10 to the -3 to 10 to the -8 millibar. And below that we have ultra high vacuum, which we consider around 10 to the -8 going down to 10 to the -11 millibar. Now I will come again to a more practical example to show you how to get from pressure to a gas quantity and to a gas flow. So we have chosen the example of gas bottles, as you can see in the picture. We can imagine that for the same filling pressure of gas bottles, but different volumes, we will have a different amount of gas included in the bottle. And then going back to Boyle's law, we consider that pressure times the volume is a constant. So pressure times the volume, we will get the unit millibar per liter. And now adding, we can add time as a dimension to that. Means when we consider a leak rate, we can consider that a certain amount of gas will escape through a leak, this kind of bottle, during a certain period of time. So then we will get our constant, which is pressure times volume divided by time. And this will give us a leak rate, which can, for example, be expressed in millibar liter per second.
Right, so this is a unit that I did not come across at school. I only learned this when I entered vacuum technology. And it can also be understood as the escape of gas. So imagine that our bicycle tire has a volume of 1 liter and we have a pressure drop of 1 millibar per second. Then this corresponds to our leakage rate of 1 millibar liter per second. And this is a defect size, which would make the bicycle tire flat in comparatively short period of time, far less than 1 hour.
Very good example to understand. Thank you, Rudi. And now we want again to compare the throughput of fluids and gases. So gases, as already explained before, the density of a gas will depend on its pressure. So therefore, we consider a gas as compressible. So again, we will have a constant, which is the pressure times volume, and a unit to describe the throughput of a gas by adding the time. So we will get units such as millibar liter per second, Pascal cubic meter per second, or SCCM, which stands for standard cubic centimeter per minute.
Yeah, life is a little bit easier with non-compressible media, liquids. So no matter whether I pour a liter of water from the next river or the next lake, or I take 1 liter out of the Mariana Trench with 11 kilometers of water pressure on it, it still stays 1 liter with a given accuracy of the measurement. So we can describe an amount of a liquid just by the volume, and the throughput of the liquid just by a volume flow of liter per second. In applications, for example, the heating, the water flow in my heating back home. Liter per second, cubic meter per hour, this would be units which are then used to express the amount of the flow. Now, what is influencing these parameters? So talking about the unit of a gas flow, millibar liter per second. We have millibar reflecting the pressure, we have liter reflecting the volume, and we have S reflecting the time. So in case that we have different volumes and identical leak rates, then of course the gas reservoir is bigger in the bigger container. So in other words, the relative change of a pressure will be smaller compared to the same defect size in a small container. So this is the influence of the volume. There is also influence of the time. So back at university, I started working with deposition systems. I did plasma CVD for solar applications. And overnight, after evacuation, we just isolated our vacuum vessel. So all the valves were closed, no pump connected any longer, no gas inlet connected any longer. And we measured the pressure rise overnight. So this long duration gave us good accuracy, but the prerequisite to do that is isothermal conditions. So small temperature variations may have an effect on the result. And this has to be considered, for example, in industrial applications of leak testing by measuring the change of a pressure. The pressure itself is also in this unit millibar liter per second, and more accurately, this should be a pressure change. The pressure that we apply is then just the driving force for the defect. So let me make a small demonstration. So if I have, for example, a small air balloon, and I apply only a little bit of pressure, yeah, it was already enough to make it fly away. So I take even less. So this is not very convincing, not a very big driving force in order to make the balloon fly. And if I give it a higher pressure, okay, then there is enough driving force in order to make it fly over a larger distance. So do not mix up the pressure as the driving force for the defect and the pressure change that you are measuring, and which is then calculated in order to yield the leakage rate in millibar liter per second. So we have tried to visualize these effects of changing volume. So in the orange graphs, you see always a constant pressure loss, constant pressure change in identical time intervals, but on different volumes. So the result is a different leakage rate depending on the volume of the container that we are in. In the turquoise graphs, we have taken always the same leakage rate. So depending on the gas reservoir that we apply, we are getting different pressure changes over time. Yeah. So same leakage rate, different volumes, different pressure change. And I would also counsel you to make graphs. Yeah? So there is a lot of information that one can extract from that. Also, the curve shape will tell you something. Non-linearities will show you that there are other influences than, for example, just the pressure.
Okay, so after this theoretical insights, we have asked ourselves on what can cause a leak, and want to give you some examples on that. So there are many potential leak generators, reasons. So here we have selected a few of them. So the first one we have selected is pitting corrosion. So pitting corrosion means that you will have on especially metal on the surface, you will have small holes in the material, and yeah, this surface defect can create leaks in your installation. Another example is during welding and soldering process. This is a source also for a lot of kind of leaks, such as let's say cracks, porosities, distortions, and yeah, this defects in the metal, for example in the volume, yeah, can again create leaks. Some very also practical example in next picture is old, let's say, defective seal. You can see it on the picture with a huge number of porosities. So this will definitely create leaks and an impact on the performance of your system and the costs. And last example, again, also very practical. We showed here a connection, an ISO-F connection, where two flanges, two connections are connected one to the other, and usually this is made with a center ring, with an O-ring in between and an outer ring, and then the two connections are screwed. And yeah, if you imagine here an assembly error, missing part, or yeah, too tightened screws, yeah, an error, again, this can be a leak source.
Right. So,
okay, so we will move further with another Paul, we are interested to see which method do you use to detect leaks. So again, we have provided some examples which you can select. So ultrasonic leak detection, pressure decrease method, helium leak detection. Perhaps you do not use any leak detection method yet, or if the method you use is not within the examples, just put your reply in the chat function again. So we are very, very curious to see what you already use as a method.
Right, the bars are moving with a clear focus on helium leak detection. Let's see how big the ratio will be for the other ones. Mm-hmm.
Oh. Okay, clear winner is here, helium leak detection, and also, yeah, a few people use pressure decrease method. Okay. Perhaps Rudy, you can comment on that in the next slide.
Yeah, thank you. So you have shown us what can be the cause of leaks, some selected examples. Our audience has told us what they are using. And let me start with the top end. So we have displayed the respective method of leak detection over a very, very broad dynamic range. So going down from the detection limit of a helium leak detector in vacuum up to very, very big gas flows. And in order to measure big gas flows, one can use acoustic methods. So yesterday I was watching football, soccer on TV, and some people will have opened a beer for that. So if you open the beer bottle, it makes thump, and this is the instantaneous release of gas which is accumulated on the top of the bottle. So this is fast escape of gas. A lot of gas is moving, and this makes a sound. So you can use acoustic leak testing and more also ultrasonic equipment. So I have just taken a small audio analyzer, and I'll show you briefly. So this is the audio analyzer, and if I now admit a little bit of gas flow, you see the frequency band moving. So this is just in the audible range, and this is also possible with more professional equipment in the ultrasonic range. The reason for these higher frequencies is also the strong direction, so the very narrow angle with which high frequency are emitted. So also from a large distance, you can have a good spatial resolution in order to see leaks in this high frequency range. And ultrasonic testing is also of very big technical importance. Just imagine that, for example, 10% of all the energy which is stored in industry is stored in compressed air. So this is an awful amount of energy. So it is of high technical importance to monitor, for example, the tightness of pressurized gases, pressurized gas supplies. If you don't do so, the compressor needs to work more. So there is a lot of energy cost, and there is also enhanced maintenance cost in case that you neglect ultrasonic leak detection. Bubble testing is probably the first method that we have come across. So I think that the majority of us has repaired a bicycle tire, and this is done by dunking, by immersing the bicycle tire under water. There is also another method of bubble testing, which is admission or using a foaming agent, for example, in order to detect escaping gases by forming bubbles in a liquid which is applied on a surface. Pressure decay is astonishingly, as a method which uses a device, less sensitive than these bubble testing methods. But still, it is the most important method for industrial leak testing, for serial leak testing. So in a modern car, there are 200 to 300 parts, and the majority of them is leak checked with, so there are more parts, but these parts are leak tested, and the majority of this tests are performed by leak testing with air. And only if you need higher sensitivity, for example, you go for leak testing with helium. Flow methods are also a subgroup of leak testing with air, but they can push the detection limits especially if you go to vacuum. So this mass extraction, which is indicated here, is leak testing with air against vacuum in molecular flow regime. Specific tracer gases are not only pushing the sensitivity limits of leak testing, but they are also allowing a large variety of methods. So if I'm sampling a gas from atmospheric conditions, for example, or if I'm measuring at atmospheric conditions, I'm typically using a sniffer probe. So I'm taking the gas probe and feed this to a helium leak detector where it's analyzed and quantified. So here I'm limited by the natural background of helium in air, which is 5.2 ppm on any place in the world, almost any place in the world. And if I remove this residual background, if I go to vacuum, I can really detect very, very low sensitivities going down to the 10 to the minus 11, 10 to the minus 12 millibar liter per second if I treat my vacuum system very well. So there are even applications which are more demanding. So for example, we have picked the solar receiver tubes on the bottom left example. So in case that you would calculate this millibar liter per second specification from the desired lifetime of the solar receiver of 20 years, the volume, which is in the lower dual digit liter range, and the pressure rise that you want to allow in this vacuum insulation of the outer tube, which is only 10 to the minus 5 millibar, then you end up with specifications which are even less than the detection limit of a helium leak detector. Encapsulated electronics, we have picked a pacemaker, so I'm very happy that helium leak detection methods do exist in order to test medical implants. My father has a pacemaker, so for me as a relative, it's very important that if he has to undergo a surgery, the device which is put into his body is tested as good as can be by helium leak testing. Also, other electronics are undergoing serial leak testing with helium. And refrigeration and air conditioning applications are often in the 10 to the minus 6, 10 to the minus 5 millibar liter per second range. Other examples are emerging technologies like batteries, like hydrogen economy. And we have picked two examples for components like an anode recirculation blower at 10 to the minus 4 millibar liter per second, and tanks 2 decades above. The detection limit of ultrasonic leak testing is somewhere in the 0.1. Some textbooks are saying 10 to the minus 2 millibar liter per second range. The majority of applications is performed at higher leakage rates. And we have put the acoustic camera, so a combination of optical methods and acoustic measurements by an array of ultrasonic detectors at 10 to the minus, 10 to the 1 millibar liter per second, 10 to the power of 0, 1 millibar liter per second. The pitch corrosion that Stephanie has introduced often generates leaks flow of 100 millibar liter per second and above. And the highest flow that we have picked is taken from the example of steel degassing, where you often have to take into account flows, process gas flows, plus leak flows in the range of 10,000 millibar liter per second. So very, very broad dynamic range. And all these leakage rates that we have summarized are of technical importance in their relevant application.
Okay, so after all these methods and applications and leak rates, we want now to come to topic 2 of our presentation, which are more real world scenarios. And before diving into that, we would like to see within the next poll in which field or application you are working, or you are from, or you are interested in. So we have selected a few of them, which is coating, chemical and pharma, metallurgy, food, or energy market applications. And if the one you are working and interested in is not in the list, again, please drop it in the chat function.
Yeah, Stephanie, I hope that we've picked some examples which are of relevance for our audience.
Yeah,
and the first click was from energy, so we have got an example from that we're going to detail a little bit later.
Okay.
And we see quite a broad distribution in the audience, which makes me happy that we did not by accident pick an example which is not represented by our user group. So roughly 50% of our audience has voted. Please take the last couple of seconds in order to to take your vote, submit your vote. 56% is not very good in democratic elections. Yeah. So
yeah, we need some more.
Yeah.
Okay, so we have here, yeah, quite, top runner is here chemical and pharma market. Lucky for us, we also have an example, let's say close to chemical market. Food also, we got an example within the next slides, and yeah, quite equal distribution between coating, metallurgy, and energy. Okay, interesting. Thank you for replying. So let's move forward with the real life examples we have chosen. So the first one is tribological coating. So means an example about functional coating process, such as, for example, PVD coating, which is used to modify physical properties of a product or material, and for example, to reduce friction, to improve resistance, or yeah, it could even have a decorative effect on the surface. So let's imagine here a condition of working pressure of 110 to the -5 millibar, a pumping speed of around 300 liter per second, and in this case, a leak rate of 310 to the -3 millibar liter per second. What would that mean in this kind of let's say process, Rudy?
The values that you have presented, Stephanie, are taken from a real example of a tribological coating. So bearings were coated, and by experience, the user knew that he needs to reach a base pressure prior to applying the process, because if this base pressure of 10 to the -5 millibar is not reached, then there is still a lot of gas adsorbed on the surface. And the result is bad sticking, bad adhesion of the applied coating. So the coating would peel off, it would flitter off, and the function of monitoring or tailoring the tribological properties of the device are not met. So the product quality is bad. You're just producing scrap. You're losing money. You cannot sell your product, and it's an ineffective use of the resources. So the product quality is really what matters here. There is no effect on for example, energy costs, electrical costs, whatever, power uptake of the pump. So this is not affected, but it's really about the product, which then cannot be sold.
Okay. Which has again an effect then on the costs. So next example comes from steel production. So vacuum tank degassing for steel degassing. So I have visited already this kind of production, and I was impressed by the huge installation and the pumping speed installed and the number of pumps in the pumping room. So it was about 100,000 cubic meter per hour, so huge installed base. The operational pressure in this case was around 0.5 millibar. And what I learned here is that there is quite a huge false airflow, which is around 50% of the total gas flow.
Yes, so first of all, what is the motivation in order to apply vacuum? So gases which are detrimental for the product need to be removed. On the one hand, this is hydrogen, which is also in ambient air. So textbooks are telling us that 0.5%, sorry, 0.5 ppm of natural gas is hydrogen. In real applications, in real world, in industrial areas, it's higher. So I've come across concentrations of up to 100 ppm. And if you have a hot melt, then it could also be the case that humidity reacts with a hot metal surface. So oxygen is incorporated into some oxides, and the hydrogen will be released. And hydrogen, on the one hand, leads to embrittlement in high-end steel, and also to delayed cracking. So the product quality can be very much improved by removing the hydrogen, as well as by removing the oxygen, because metal plus oxygen gives an oxide. So there will be non-metallic inclusions which have a bad effect on fatigue strength. So steel products which are exposed to high mechanical stress, crankshafts, for example, they need this type of processing in order to achieve the desired product quality. And I've learned that, as you said before, 50% of the total gas flow in the range of 5,000 millibar liter per second are false air flows. Yeah, so imagine one could reduce this. This would be a major cost saver, because you could have lower initial costs by making the pumping system smaller. You would have much lower power uptake. So one of these pumps can have a power uptake of something like 15 kilowatts. And we're talking of dozens of pumps of that size in a steel degassing system. And of course, if you save amount of pumps, you can also save on maintenance costs. Unfortunately, this is difficult to achieve because at a certain point of time, this melt has to be poured out of the crucible. And at this point, you are necessarily generating layers on your sealing surfaces, and these are responsible for this extremely high false airflow. So difficult to avoid, but it would really be worth an effort.
Okay, impressive, really, the impact on leaks in this kind of application. Another one we have chosen is are explosive environments. Considering explosive environments, what is highly important is to assess the risk of oxygen increase or oxygen entering the system through a leak. So again, we will have consequences in case there are huge leaks, or yeah.
Exactly. So if I'm creating a potentially hazardous atmosphere, I need to change my pumping equipment. I cannot live with a standard pump any longer, but the higher the risk, the more I need to monitor the process, and I also need to equip my pumping equipment according to the needs of the potentially hazardous gas composition in my process. So I need, for example, to add monitoring, I need to add gauges, I need to modify the surfaces, I need to code, I need to prove that some explosion, some burst pressure will be withstood, and so on and so on. So the initial cost, according to this preparation for explosive atmospheres, is not negligible, can be an awful lot of money. And also approving the suitability of the modified pumping system can be a major cost add-on.
Okay. Next example for the people who have selected energy in the poll, which may interest you. So we've chosen the example of a power plant here. So first of all, short explanation on very simply how that works. So in the power plant, the burning of fuels, which couldn't be oil, coal, or LNG, for example, liquid natural gas, fires a boiler in order to generate high temperatures and high pressure steam. This steam is then used to drive a steam turbine, and a generator is attached to this turbine. So in order to generate electricity, in case of leaks here, what will be the impact, Rudi?
So if I have a leak, the pressure in the condenser may rise, meaning that also the backing pressure of the turbine is rising. Now, the efficiency of the turbine is a function also of the pressure that you have in the condenser. This is individual for each type of turbine, but if you calculate the cost per kilowatt hour from the efficiency of the turbine, or the efficiency change of the turbine, the fuel cost, and also the power rating of the turbine, you end up with something like 0.00 something euro cent per kilowatt. This may sound a tiny amount of money, but imagine that you have a very high uptime of the power plant of more than 8,000 hours per year, and you don't have kilowatt rating of the power plant, but for example, a big current nuclear power plant would have a power rating of 1,400, 1,600 megawatts. And for example, Germany's biggest coal plant has a rating of 4,400 megawatts. So we are multiplying this tiny fraction of euro cents per kilowatt with very big numbers, and this results in financial losses in excess of 100,000 euro per year. So a very small efficiency change in the turbine costs an awful lot of money. And we are really talking about hundred thousands of euros per year. So it's very important to keep the integrity of the system in order to keep the efficiency of the turbine high.
Okay, interesting example. Last one we have chosen is drying food for additives, for example. Means that, for example, chemicals are added to food in order to enhance the flavor, the texture, and in general, for example, freeze drying is used for that. We can imagine here a pressure of 1 to 5 millibar, and imagining a leak which will raise the pressure to 20 millibar. What will happen, Rudy, in this case?
Yeah, this is also a real example. So the reduced uptime as a consequence was here before the application, but the result of this enhanced pressure is a poor drying efficiency. So you still are in the range of the vapor pressure. So the humidity does not leave the product very well. So the product is bad itself, and if you process the product, you crush it at a later stage after the drying. So the crusher is then blocked by this humid product. You have higher process pressure, so you have higher energy costs with the pumps that you're applying, and this also results in shorter maintenance intervals, higher maintenance costs, and of course reduced uptime again. So in this real example, the dryer was equipped with dry pumps in the range of 600 cubic meters per hour. So a potential solution in order to get to the desired pressure would be adding pumping speed. This is in favor of our business model. So please, dear customer, do so. No, seriously. So this is not the right way to go. So adding pumping speed is not necessary if you control your leaks. So also reducing the leakage rate and achieving a lower pump size still needs to be done in a way that the desired process pressure can be achieved. In our case, it was done by fixing leaks, by tailoring some of the non-vacuum type equipment, enabling it to operation in vacuum, and then the designed pumping capacity of 600 cubic meters per hour is sufficient to do the job and provide a reliable product quality. So the pump which was used is the one in the middle in this example that we have just gone through. We have picked two other examples and other leak flows. So we're starting with a very small pump, 6 cubic meter per hour scroll pump with a leak flow of 100 milliliter per second. And we have taken twice this gas flow for the other two applications, a dry pump on its own and a combination of a dry pump plus a roots pump.
Yeah, we have made here a few calculations. So with the first example, which is a small scroll pump, as Rudy already mentioned, of 6 cubic meters per hour nominal pumping speed, imagining a 100 millibar liter per second leak, you can see on the curve that the power consumption will rise. Yeah, doing a calculation with like an industry energy cost of 17 cents per kilowatt hour, this will come to cost of 95 euro per year, considering an operation 24/7, so all the time. In the next example, we looked at a much bigger pump, which is a dry screw pump with a nominal pumping speed of 400 cubic meter per hour. Bigger motor installed on this pump. Here we did a calculation with a leak rate of 200 millibar liter per second, and as you can see, the impact of quite big leak here impacts much more on costs. You have already 565 euro per year for only one pump. And in the last example, we added on the top of this screw pump a roots pump. So we get a combined pumping speed of 3,600 cubic meters per hour. We have chosen the same leak rate, so 200 millibar liter per second, 24/7 operation during the year. And yeah, with this quite big leak rate, we already raise costs for nearly 4,500 euro per year. And this is only for one pumping station. So imagining a production site with several of these, impact of a leak is huge to the energy consumption.
You could buy a very good vinyl record player for this amount of money.
Exactly.
Yeah. So what do we recommend you to do in order to avoid leaks, to address the problem of leaks? So first of all, you need to know what is detrimental for your process. So you need to define a criterion for tightness. So then select the right technology in order to monitor, to measure what you need to measure. So select the right technology with respect to, for example, sensitivity, to information content, to environmental influences, and so on. Also define time intervals when you want to either permanently monitor changes in your process, or do you need to do measurements in intervals in order, for example, not only to measure leaks, but also to provide for safety aspects. So this is regulation in chemical industry, for example, to check isolation valves and so on in regular intervals. So how do you want to recognize a leak? Permanent monitoring could be pressure monitoring, it could be power uptake monitoring of a vacuum pump, and there are various other methods that you could apply. If you do leak testing by pinpointing, of course, helium leak detection is best, giving the broadest range of methods that you can apply, and also providing a very, very big dynamic range. So we have seen examples over, I think it was 16 decades before, and this is the whole range that you can use a helium leak detector for. Of course, a helium leak detector is not a cheap instrument, so you could buy a very, very, very good record player for that, for the prices of a helium leak detector, maybe a full stereo equipment. And there are also other alternatives, cheap alternatives. As I mentioned before, I did pressurized tests overnight when I was back at university time. And this also applies for current industrial applications, and other localizing methods could be using the cheaper methods of foaming agents and so on. So very cheap soaping solutions. Ultrasonic screening, high-end equipment may even reach the cost of a helium leak detector, but it combines measuring and also visualization of the defects in a limited dynamic range. So what do you need to do in order to select the right technology? First of all, what is the pressure gradient? Do you have an inside out or an outside in method? So do you have a device which is under overpressure in real life operation, or do you have a vacuum system? What do you want to do? Do you want to measure a leak, or do you want to localize a leak? For maintenance applications, localizing in the majority of cases is sufficient. Then do you want to do an integral method or a partial method? Do you need to measure the total area or local area? So the whole surface of a device, for example, you've been talking about pitch corrosion. Do you need to cover the whole floor, or is it sufficient to check the well seams of the floor? Open question, your task to decide. And then what is the desired sensitivity limit that you need to measure? So all this then leads to selection of the right method with the right equipment. So thank you very much for staying with us the last 3/4 of an hour. So we've gone through fundamentals with definitions, units, potential causes for a leak, and also an overview about detection technologies. We've picked some real life examples from the mentioned applications, fields of applications, and I can only encourage you to take actions. Roughly 10% of you have mentioned that you don't do any leak detection. Get going, yes, and select the right technology. Do not forget to invest also money into the education of the right stuff, but this will be overcompensated by the money that you are saving, by saving product quality, by saving on energy costs, maintenance costs, and other cost adders.
Okay, thank you for the summary, Rudy. So again, just as a reminder, if you want to receive the slides of this presentation, just take part in the survey and click yes to receive them. And now at the end of the presentation, we want to have a look to your questions. So let's start with them. I will have a look. So I have here a first question, very interesting question. I have cleaned my system ever since the leakage rate is higher. Why?
The question is, how did you clean your system, and how did you measure this? So cleaning normally should have a positive effect. Yeah? But if you do some wet clean, for example, and you measure with a pressure rise method, so then you may still have residuals of humidity. So this is then released and leads to a higher pressure in the pressure gauge. But if you do this repeatedly, it should vanish, because then if you make a pressure rise test, evacuate, vent again, then this humidity is flushed out, and repetitive tests should yield a lower result.
Okay. Thank you, Rudy. Next one, there are quite a few of them. So next one is there a possibility to convert a leak rate from 100% helium to hydrogen? Tough question.
In principle, yes. So in the majority of applications, in many technically relevant applications, we are in laminar viscous flow regime. So the message is we need to apply theory. And if we apply, for example, laminar viscous models to calculating leak flows, yes, you can convert from medium A to medium B very generally, because what is the only parameter which is influencing the result with respect to the test medium is the dynamic viscosity of the test medium. So just taking the inverse ratio of dynamic viscosities allows conversion from medium A to medium B, as long as we're talking about gaseous media. Please get in touch if you want to learn something about the conversion from liquids to gaseous media or vice versa.
Okay, thank you. Another question here is there any other gas that can be used as an alternative to helium? If yes, are those expensive than helium, like argon or something like that?
Depends on what you want to do. So helium has a unique combination of a very sensitive detection technology, very high selectivity. It's environmentally friendly, so I can release it without any consequences. It's innocent, so it does not lead to embrittlement like hydrogen does. For example, we had the example with steel. It is permitted to be added to food, to pharmaceuticals, and so on. And the selectivity of the detection is unrivaled. So this combination of all these parameters can only be achieved with helium. If you can compromise on some of these, then you can use other tracer gases. So for example, hydrogen is used as a process gas, also as a test gas when it's used as a processing agent. Diluted hydrogen is used as a standard gas, for example, forming gas, 95% nitrogen, 5% hydrogen is used, but only in sniffing methods and with reduced sensitivity compared to helium. And you've mentioned argon. So if I want to measure argon at ambient air, of course, I have a much higher background, because 0.9% of ambient air is argon. So compared to the 5 ppm of helium, we have a much higher background. And also talking about the detection technologies, for example, if you have an oil-sealed pump for your detector, then hydrocarbons, C3 group, so propane, this will then interfere with the mass signals of argon. So yes, limited applications are possible with alternative gases, but still, if I want to save cost, for example, if I want to go away from 100% helium, I would rather think about diluted helium. For example, there are welding gases which are having helium concentrations between 5 and 30%. So I would rather think into this direction than going completely away from helium.
Okay. Thank you. You have just mentioned sniffing, Rudy. This goes very well with the next question I have here, which is, what reliable detection range does a sniffer have?
So if I consider, for example, again, it depends on the application. So sniffing is by definition a localizing method. And sniffing with helium is limited by the natural concentration of helium in air, which is 5 ppm. So imagine I take one of our standard sniffer probes, which has a throughput of 1 millibar liter per second. Then I have 5 ppm, dimensionless concentration, times 1 millibar liter per second, which is 5 times 10 to the minus 6 millibar liter per second as a flow. So if I want to be more sensitive, I need to reduce the flow, but this goes along with the request for much more careful working, because if I reduce the flow of a sniffer probe, then I have a lower background, but I need to be very much closer to the defect. So I need to work slower, I need to work more accurately, I need to be directly on the surface. So this is not necessarily matching the needs for production or for efficient, fast localization of a leak in order to repair it. So for example, there are sniffer probes on the market which are having hundreds of SCCM, so dozens of millibar liter per second, and the highest sniffer probe flow that I'm aware of is 3000 SCCM, which goes along with a helium background in the 10 to the minus 4 millibar liter per second range. So it's not only a question about sensitivity, it's really a question about the demands of the respective application.
Okay.
If there is a special case that needs to be discussed, please get in touch directly and we can talk about this.
Yeah, exactly. And here I would say the last question I got is very interesting real life question. What is the best way to find a leak in a large vacuum piping network while the plant is operating? So with a high volume noise volume, sorry.
It depends on the sensitivity that you need to check. So if the plant is in operation, then obviously you don't get the time to shut down the plant, to empty the plant, to fill it with helium and so on. So then you are limited to the methods which do not need any preparation, which can be applied during continuous operation of the plant. And this would be, on the one hand, ultrasonic screening, or on the other hand, the use of foaming agents. So these are the only two methods that come into my mind for this demand, but then of course you are limited in sensitivity compared to tracer gas methods. So again, if you want to discuss this this specific application face to face, drop us a line, please.
Yeah, we would be happy to to receive your questions even after the session. So that's it for today. Thank you again for your participation, and if you have colleagues who also want to log in, please note that there's another session this afternoon at 5 p.m. So we will be happy to see even more people there. And thank you again very much. Thank you, Rudy, and see you later.
Thanks to you, Stephanie, and thanks to you out on the screens. Talk to you.